Hello there, and welcome to our AP review of topic 8.4, acid-base reactions and buffers, part 2, weak acids reacting with strong bases. So in this video, we're going to talk about what a reaction looks like when a weak acid reacts with a strong base, and then we're going to calculate the pH of resulting solutions when we have excess acid reacting with a strong base, and in a second problem where we have excess base reacting with the acid. So when a weak acid and a strong base react with one another, weak acids are written in the molecular form as hydrogen bonded to some anion. And this is a generic way of writing a acid, which is an aqueous solution. A strong base, which is a metal bonded to hydroxide, can be written as MOH, which is also an aqueous solution. And when these two react, it's a double replacement reaction, and we'll end up making a salt, which is a metal anion, and water, which is HOH, or H2O, which is a liquid at room temperature. Now, when we write the ionic equation for this, because chemists actually typically want to look at the ionic equation, weak acids and weak bases are written in the molecular form in the ionic equation. So HA, our weak acid, is still going to be written as HA. Our strong base ionizes completely or dissociates completely, and so the metal and the hydroxide are going to be written as ions in solution. Our salt is going to be written as ions in solution as a soluble salt, and then we're going to produce water as a liquid in the solution. To write the net ionic equation, we're going to cancel out our spectator ion, which is our metal ion. And so the overall reaction for a weak acid reacting with a strong base is the weak acid reacting with the hydroxide from the strong base to produce the anion in solution and water. And so this is our net ionic equation for this reaction. Now, if we want to determine the pH of the resulting solution, we need to know whether we have excess acid or if we have excess base, because whichever substance is in excess is going to be the substance that determines the pH of the solution. Remember, when we're solving for pH, the pH is equal to the negative log of the hydronium concentration. So at the end of the reaction, our goal is to find out how much hydronium is present in the solution. And that hydronium is either going to be due to our acid being left over, our base being left over, or even our conjugate base being left over. And so let's go ahead and take a look at a couple of practice problems and see how to solve for the pH of a reaction between a weak acid and a strong base. So here's our first problem. We're going to solve for the pH of a solution that's created when 0.5 liters of a 1.20 molar hydrofluoric acid, which has a Ka of 6.60 times 10 to the negative 4, is combined with 1 mole of sodium hydroxide. And we're going to assume that the sodium hydroxide doesn't affect the volume of the solution. So the first thing I want to do is write the equation between these two substances. So our first step is we want to find out what our initial moles of each substance are. And so I'm going to write a table where I'm going to write my initial moles of acid and initial moles of base, because we need to know which substance is the excess reactant, and which substance is the limiting reactant. So we are given the moles of the base, so we don't have to do any calculation here. We have 1.00 moles of our base. But we aren't given the moles of our hydrofluoric acid. And in order to determine which one of these reactants is in excess and which one's limiting, we need to know the moles of each substance. So to calculate the moles of HF, I'm simply going to take the liters of the HF solution and multiply it by the molarity, because my molarity times liters gives you moles. So 1.2 times 0.5 is 0.6 moles of HF. So I have 0.600 moles of HF. Now notice they're reacting in a 1-to-1 ratio. So the substance that I have less moles of is going to be my limiting reactant. It's going to limit the extent that this reaction can take place. I have excess sodium hydroxide. So it is going to react with the limiting reactant. So our change in moles is going to be a complete reaction of our limiting reactant, which is going to leave 0 moles of our limiting reactant left over. And then in a 1-to-1 ratio, we're going to lose 0.600 moles of our excess reactant, which is going to give us 0.40 moles of sodium hydroxide left over after our reaction takes place. So we have extra sodium hydroxide left over. For our sodium fluoride, we have none initially. We're going to gain 0.600 moles of sodium fluoride, so 0.600 moles of sodium fluoride. And then the water, we don't really care about because overall it is not going to affect the pH of the reaction with these concentrations or these amounts of acid and base present. So we've got our base left over, and we have some conjugate base. Which one of these is going to affect the pH most? Well, remember, conjugate bases only react to a very, very small extent, and so that is not going to affect the pH very much. The pH is going to be determined mainly by the leftover sodium hydroxide. If you recall from a previous video, if you know the concentration of the strong base, that is the concentration of the hydroxide because strong bases dissociate completely. And if we know the concentration of hydroxide, we can use that to determine the concentration of hydronium, which in turn we can use to determine the pH. So how are we going to determine the concentration of the hydroxide? Well, concentration is equal to moles divided by liters. We know the moles of sodium hydroxide, 0.40 moles, and we know the liters of solution, 0.500 liters of solution. And so 0.4 divided by 0.5 is 0.80 molar. So this solution is 0.80 molar hydroxide. Now, if you recall, we can calculate the pOH of our solution by taking the negative log of the hydroxide concentration, and then we can use the pOH to determine the pH. So the negative log of 0.80 molar is equal to 0.0969 for our pOH. And that makes sense. The pOH would be very, very small for a strong base. So to determine the pH, we're simply going to use the equation pH plus pOH equal 14. We simply plug in our pOH to get our pH. So 14.00 minus 0.0969, which gives us a pH of 13.90. So our pH is 13.90 for this particular solution, which again makes sense, a very high pH, given that it is being determined by a strong base. So that's a reaction where you have a limited amount of weak acid reacting with an excess amount of strong base. What about if you have excess acid? How are we going to solve that problem? Here's the second problem where we're going to determine the pH when we have an excess amount of weak acid. So again, I'm going to write the equation. For this one, I am going to write the net ionic equation. So the net ionic equation is our hydrofluoric acid reacting with hydroxide to produce fluoride ions plus water. And the reason for this is because this conjugate base is going to be really important in this particular reaction. So that's why I'm writing it as a net ionic equation so I can see the conjugate base very clearly. So again, we need to determine which substance is in excess and which substance is limiting. From the previous problem, we learned that if we multiply the molarity times the volume, we can get the moles of our acid. So our moles of acid are 0.600 moles of acid, and that's 0.5 liters times 1.2 molar. Our base is, we're already given the moles. We have 0.120 moles of our strong base. We don't have any conjugate base initially, and so I have 0 moles of conjugate base initially, and water is not going to affect this problem, so I'm going to ignore water in this problem. So change. How much is this all going to change by? Well, again, the limiting reactant is going to run out first. We can only make as much product as we have limiting reactant. And so our limiting reactant, if you look at our mole ratio here, we have less moles of base than we do of acid. So we're going to react 100% of the base, and we're only going to lose 0.12 moles of our acid because the limiting reactant limits how much product you can make. We are going to gain stoichiometrically 0.120 moles of our conjugate base. And so for all of our reaction here, 0.6 minus 0.12 is 0.480 moles of our acid are left over. We don't have any moles of our base left over, and then we have 1.20 moles of our conjugate base remaining. So to solve this problem, our pH is going to be determined by the acid that remains and the conjugate base that's present in the solution. Remember, this is going to set up an equilibrium between these two. So how are we going to determine the pH? Well, we can use the Henderson-Hasselbalch equation. If you recall, the Henderson-Hasselbalch equation says that the pH of a solution that has both acid and its conjugate base present is equal to the pKa of the acid plus the log of the conjugate base concentration divided by the concentration of the acid. This is the Henderson-Hasselbalch equation. If we have both a weak acid and its conjugate base present simultaneously, then we can calculate the pH of the solution if we know the Ka. So first, let's calculate the concentration of our HF and the concentration of our F. The concentration of our acid is the moles of our acid after the reaction, which is 0.48 moles, divided by the volume of the solution, which is 0.500 liters. So 0.48 divided by 0.5 gives us 0.96 molar. So that is the concentration of our acid. The concentration of our conjugate base is the moles of our conjugate base after the reaction, which is 0.12 moles, divided by the volume of the solution, which is 0.50 liters, and that gives us 0.240 molar. So now we know the concentrations of our acid and our conjugate base, and we can plug that into our Henderson-Hasselbalch equation. So the pKa of our acid is the negative log of the Ka, which is 6.60 times 10 to the negative 4, plus the log of our conjugate base, which is in the numerator, 0.240 molar, divided by the concentration of our acid, which is 0.960 molar. And if we solve all of that, we will get the pH of this solution, which is 2.578 for our pH. So that is how to solve a problem for weak acids reacting with strong bases. If you want to see how other types of acids and bases react, please watch the other videos in the 8.4 series.